All right, now that you have sufficiently reviewed molarity and dilutions, we're going to talk a little bit about Beer's law. Before we do that, though, I want to mention that there are two types of dilutions you can perform in a lab setting. There's what's called a serial dilution, which is where you have your stock solution or the original concentration from whatever your instructor provides you. And then you take a prescribed amount out of your stock solution by pipette. And so this particular example is showing that you would take 1 milliliter out of the stock solution and transfer it to a new test tube. And then you add a prescribed amount of water to dilute that down. So here we're looking at taking 1 milliliter of stock, adding 9 milliliters of water to have a final volume of 10. And so that means this is diluted by 0.1 of whatever the stock solution was. And then you can then take 1 milliliter of this first dilution and transfer it to a new test tube and add another 9 milliliters of water, which means we have a 0.01 of our stock per volume solution. And you can kind of continue this on. And so this is called a serial dilution because we do this in series. There's another way to do a dilution. You can't see my stuff, which is called a parallel dilution. So if you can imagine, you take your stock dilution and you dilute it in a 1-to-4 ratio. And that could be like take 1 milliliter of stock and add 4 milliliters of water. And then in the next test tube, you would take 2 milliliters of stock and add 3 milliliters of water. So that's a 2-to-3 dilution ratio. And then the next test tube would be 3 milliliters of stock to 2 milliliters of water, and so on and so forth. This is the type of dilution we would be doing if you were doing this lab in person. This is the type of dilution I did to prepare the take-home lab kits for you to perform this lab at home. So let's talk a little bit about light and concentration. White light, or if you just think of like the light that comes from the sun, consists of all colors of the rainbow. It's a big mush of all the colors. So Roy G. Biv, right? And objects, when your eye perceives the color of that particular object, it's because they absorb all of the colors except the ones that your eye sees. So, for example, this test tube of bluish greenish solution absorbs all the colors of the rainbow with the exception of blue and green, which pass through, those colors of light pass through the solution, and that's why you perceive it as being a bluish greenish turquoise colored solution. You can test this, and if I have the time, I will do a quick little demo where I take like colored water. So if you have like a kitty laser or something like that, which usually is like a red laser pointer, easy to obtain. Some people have those laying around their house. Get you some water and put it in a clear glass and add a couple drops. It doesn't take much of red food coloring. And then get another glass of, say, blue water, and shine the laser through and hold like a white piece of paper or something up on the other side. You'll see that the red laser maintains its intensity, or pretty close to its intensity, through the red solution because the red solution doesn't absorb red light very well. But it loses some of its intensity when you shine it through blue solution because the blue solution does absorb some of that red light. So the tool we can use to measure this and obtain some data is called a spectrometer. There is an app that you can use on your phone to kind of mimic this, but all it really is a light source that provides some white light. And then we shine it through a sample, and we need a detector on the other side. And so this can be as simple as what is sent home in the take-home lab kit, which is me asking you to use a light source that comes from just a piece of construction paper with light reflected off of it. And the detector is going to be an app in your phone. You're going to use your camera to detect the amount of red, green, or blue light that passes through a particular solution. So it's really simple. If we're doing this in the lab space, we're going to use what's called a colorimeter, which is kind of a simplified version of a spectrometer, but it does the same thing and allows us to measure the same values. So the mathematical relationship we're going to be looking at is what's called the Beer-Lambert law, where big A represents absorbance, meaning the amount of light that is missing once it's transmitted through a substance. So thinking back to that example about shining a red laser through a blue solution and it loses some of the intensity because the solution itself absorbs some of that red light. The detector on our spectrometer can measure that, and it reports a value out to us called absorbance. Absorptivity or molar absorptivity is a constant specific to the substance. So if we're using food grade dye that's blue 40, then the absorptivity of that is a constant value, and I'll provide you with those absorptivity values. Path length is the distance that the light has to travel through a sample. So typically we use cuvettes, which are 1 centimeter in path length, but the path length can vary. And then concentration, of course, is the molarity or the ratio of moles of solute per liter of volume. So absorptivity, we can measure this, although we're not going to need to measure this, but what we're looking for is what's called lambda max, or if you recall, lambda is the variable that we use to represent wavelength. So lambda max means the maximum wavelength where light is being absorbed. And so when we're choosing a light sample or a color of light to shoot through our solution, we want to choose one where it has high absorbance because that's going to give us the best value. So if in this particular graph, I asked you to choose the wavelength of light that's going to give you the best absorbance data, you would predict that we would want to use light somewhere in the 580 nanometer range because that's where the peak of this graph shows us. That's the lambda max. So if we're sending this light through a sample, we want to send light that's kind of in that yellowish orange color through the sample because it's going to absorb. We wouldn't want to send blue light through a blue sample because blue light won't be absorbed by a blue sample. So path length, what does that have to do with anything? Well, if you think about these blue dots in this picture representing moles of solute in that substance, and the blue arrow is the light that's going to travel through that substance, if the light has to travel a further distance, it makes sense that it's going to interact with more moles of the solute. Therefore, more of the light would be absorbed. So as you increase the path length, the absorbance also goes up. So again, we typically use what's called a cuvette, which is a little plastic rectangular prism that we can put our solution in that are 1 centimeter in by 1 centimeter for the size. The path length is going to be 1 centimeter. Concentration, how does that affect absorbance? Again, the blue arrow represents light and the blue dots represent moles of solute. So the top box shows us that we have a lower concentration. The bottom box shows us that we have a greater concentration. If we send our light through that top cuvette, then it has a less likely chance of being absorbed by the moles because there's less of the moles of solute in that solution. So the absorbance would be much lower if we compare to the bottom box. By increasing the concentration, we're going to increase the likelihood that the light source is absorbed by the moles of the solute. So the absorbance would go up. As you increase concentration, you also increase the potential for error because once light is interacting with those moles of solute, it has the potential for bouncing off and scattering, which makes the detector struggle to read those absorbance values. So we typically only accept absorbance values up to 0.9 and not much higher than that. If we have absorbance values greater than 0.9, that means our concentration is too concentrated and we need to dilute our solution and try again. Okay, so quick kind of checkpoint question. What color light will be absorbed by this blue solution? And the answer is all the colors except blue. We see this as blue because it emits blue light, but it absorbs everything else. So if I send a point of red laser or a green laser or an orange laser through this light or through this solution, then I'm not going to see the same intensity of that laser pass through to the other side. But if I point a blue laser through this light or through this solution, if I put blue light through the solution, then the intensity of that blue light would pass right through because the solution does not absorb the blue light. Here's a calculation question. So let's say we have a 1.00 times 10 to the negative 6 molar solution of PbNO3 That's lead nitrate. And it shows the following absorption at different wavelengths. The spectrometer uses a 2 centimeter path length. Determine the absorptivity for the solution at 635 nanometers. So what we need to know is what color corresponds to 635 nanometers. So you have this table over here, and it looks like red has 635 or orange. So those are kind of on the cusp at those particular wavelengths. So if we look at the absorbance of the light through the solution of the various substances, orange is actually not an option. So that leads me to believe that I'm going to use the absorbance for red. And so if big A equals little a, b, c, then I just simply algebraically plug these numbers in, where molarity is concentration, path length is B, and the absorbance is big A because we are solving for absorptivity, which is little a. So plug it in, and algebraically, I get that the absorptivity is 175,000. So rule of thumb for selecting your wavelength for the color of light that you want to choose to send through your sample. So essentially, you want to select something that's as opposite on the complementary color wheel as possible. So down there in the bottom, there's a color wheel. And so if I was using a blue solution, I would want to select orange light to send through that solution. That is why the take-home lab kit has a piece of orange construction paper, because that's going to provide your light source for your blue solutions. If we were testing, say, red solution, we would have selected a green light source. But basically, here's kind of an easy way to remember that. If you write out Roy, G, Biv, and stack them, these are kind of the opposite ends of the color spectrum. So if I'm using blue solution, I'm going to select orange light. If I'm using red solution, I would select green light. If I was doing something with a violet solution, I would select yellow light to get the maximum absorbance possible. So ultimately, the goal here is we're going to create a calibration curve to determine the concentration of dye in an unknown Gatorade solution. And the reason this works, we're going to use blue Gatorade. Here in this example, they're talking about this red Gatorade. Because the fierce red Gatorade, the only thing that colors this Gatorade, the only thing that provides the red color is one type of red dye. The only thing that provides blue color to the blue Gatorade that we're going to be using in our lab is one type of blue dye. And so those work well because we don't have, it's not a mixture of dyes. So if it was like a like lemon lime Gatorade, they use more than one type of dye to get that particular color in the lemon lime Gatorade. But in Fierce Red and the Glacial Freeze Blue Gatorade, it's only one type of coloring. And so that's the only thing in the solution that has coloring. And so that's what we're going to manipulate in our lab using the colorimeter. So what we do is we take a dilution of just colored water using that exact same type of dye. So we do a parallel dilution where we get, 4 or 5 dilution samples, and we measure the absorbance versus the concentration. We calculate the concentration. We must first know the concentration, and then we use the software to obtain the absorbance. And we plot those pieces of data, and we get a linear relationship when we plot absorbance versus concentration. And from that linear relationship, we can get a y equals mx plus b of this line, where y is the absorbance and x is concentration. So if you think about this, we said A equals ABC, and if B is 1 in Beer's law, then really we have A equals absorptivity times C. And I know in this particular example, the y-intercept is showing to be 0.0088, but logically it would make sense that our y-intercept should go through the origin, because if I have a concentration of 0, aka water, then it would make sense that there would be 0 absorbance in that light. So we should force our graph to go through the origin. And so then we can kind of ignore this. Let me get my pointer back. We can ignore this B value. And so if we ignore this B value, because this technically should be 0, then we get Y, or A, because that's our Y, equals slope times concentration, or C over here. Well, what does this slope represent if we think about that Beer-Lambert law, that A equals ABC? The slope is really just absorptivity times path length. Well, if path length is 1, then the slope corresponds to the absorptivity. So the cool thing about this is if we plot a calibration curve for what is the absorbance of light against multiple concentrations of red dye, in this case, then if we take a sample of this Gatorade, and the Gatorade's got all kinds of other stuff in it, when we plotted this calibration, we were just plotting red dye and water. But if we take a sample of this Gatorade, if we can measure the absorbance of that, we now have an equation where we can plug that absorbance in for Y and solve for the concentration at that particular absorbance, because this is a linear relationship. So this says, what is the concentration of red dye if the Fierce Red Gatorade has an absorbance of 0.37? So we simply take that 0.37, plug it in for Y, solve for X. Easy enough. And I actually haven't done that, so I'll leave that to you. But if you have questions, please reach out. Okay, so briefly, transmittance versus absorbance. So what the spectrometer really measures is transmittance, and I'll let you read this on your own. The relationship between transmittance and absorbance is absorbance equals negative log base 10 T, where T represents transmittance. Transmittance is technically what the colorimeter measures. It's how much light is transmitted through the solution, and then it does this calculation for us within the equipment to spit out what absorbance is. So say you get a question that says, if the absorbance of a sample is 0.85, what is the percent of light transmitted through the colored sample at this collected wavelength. Well, absorbance equals negative log base 10 of transmittance. So you just plug in and then convert to percentage. Plug this in for A, for absorbance, solve for T, and then convert to percentage. Okay, so for the lab, if you're doing this in class, I will ask that you go ahead and do this parallel dilution of the stock solution. I'll provide you with a lab handout for that. You're going to measure the absorbance of each of those dilutions that you prepare. I'm going to show you how to use the Vernier software to create a linear regression of those absorbance versus concentration data. Then I'm going to give you a sample of your unknown Gatorade, and you'll measure the absorbance of that. And then using that example with the linear regression, you'll determine the concentration of the unknown Gatorade. If you are doing this from home, I have already prepared the parallel dilutions for you from the stock solution, and I've labeled those. And you will follow the handout and the video guide that I'm going to send with you to measure the red, green, or blue light using your phone, and then plot it so that you can make a linear regression and determine the concentration of your unknown as well. Thanks.